Lesson 10.1, sample spaces. So module 10 is about probability here. All right, so 10.1, we're looking at experiments. So an experiment is a situation involving chance. We have outcomes. Right? We got the spinner right here. We got another example. We're going to toss a pair of die. So if you're playing with dice, right, if you like flipping a coin here, right, I could do roll this ball that has 100 numbers on it, 100-sided die. Right, we're looking at number 87 right here. Right? And so how could you define a sample space? Well, if you're looking at the spinner right here, what we've got a red space, a blue space, and a purple space, right? They aren't all even, but, okay. The sample space for flipping a coin here might be heads and tails, and that's it. Right? Flipped it, came up in heads. Rolling this 100-sided die, the sample space could be 100 numbers. Okay, now rolled number 7, so 1 out of 100 chance. Okay. What else they got about this? No, it could be a finite sample space. I just did so many examples of those with you guys. There could also be an infinite sample space. And they have a couple of examples of those they broke down further. So if it's discrete, for example, it said tossing a coin until you get 2 heads, maybe two consecutive heads, maybe, right? So you could keep flipping this coin, and is it possible that you flip this 100 times and it shows up on tails, right? Like you don't get 2 heads or 2 heads in a row, right? Or how about 1,000 times? Now the chances of that would be tiny, 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 but not actually zero. So technically infinite, but discrete because there could be like heads and tails. You could count those. How about infinite continuous? The example they gave is all diameters of a circle. Well, yeah, if you're talking about diameter, you could really break it into any length, right? Unless you talk like Planck length or something. Right? You could, if you're talking about within the real numbers, right? Maybe you can have a diameter is like 5.5842307 centimeter. However, you get however long you want to stretch that number. Right? So we got finite, we get different kinds of infinite. All right, so let's look into these examples, right, and then eventually do some puzzles from the main puzzles. So example 1, define a sample space. A fair die is tossed once. Right, fair die. What is the sample space of the experiment? And so, well, you could get any number 1 through 6. So you list it as, bright list so it shows up bigger on the screen. Example 1. So toss a die. Right? So the sample space, we call it S, equals. Right? Now this is discrete, so use curly brackets and list out all the possibilities. You might roll a 1, you might roll a 2, and so on, all the way up to a 6. There's your sample space. Okay? Next question. What is the sample space for the event of rolling a prime number? Ooh, write the outcomes. Okay? Now, here they're implying that there's going to be 3. Okay, so all outcomes here. Okay. Yeah, let's do a die for a prime number. Okay, so we got a different sample space, right? Well, let's look back at this list. So by definition, 1 is not considered prime, right? But 2 is, 3 is, and so is 5. So I think those would be your prime numbers, 2, 3, and 5. Okay? 4 is not prime because it's divisible by 2. 6 is divisible by 2 and 3, also make it not prime. Okay, so there's your sample space for rolling a prime number. Example 2, represent a sample space. Yeah, Kimbei has a black hat and a red hat. He chooses one hat for each day, Saturday and Sunday. Represent the sample space for this experiment by making an organized list, a table, and a tree diagram. So let's start with the list. So example 2, we got list. Okay, and I started the list for you. Okay, so we got sample space equals, okay, curly brackets because it's still discrete. Okay, but we got 1 on Saturday, 1 on Sunday. Okay, we got black and red. Okay, well they started first here, so they said it could be red Saturday and red Sunday. Okay, so that would be one possibility. Okay. Maybe he does red Saturday and black Sunday. That's a possibility. Maybe he does black and black. Right. So there's 3 possibilities. But it says there's well, there have to be at least one more, right? Because what if he wears black on Saturday and then red on Sunday? Okay. And I think that would be it, right? I don't think there's any other possibility. So that would be a complete sample space. Okay. Now there might be a better way to visualize this too, and that's with a table. I like this table. So let's go table. Okay. This is probably how I would organize this in my mind. Is you got let's do Sunday on this axis and Saturday on this axis, okay, to also match their table. Okay, and each of those days you could choose to wear either red or black. So put red and black Sunday, red or black Saturday. Okay, okay, so now we're going to get the same outcomes before, but just the same sample space, just different way of organizing it. Okay? So we could wear red each day, red, red. That's like this one right here. Boink. Okay? You could wear red followed by black. That would be this one right here. You could do, well, black, black would be this one. Right, so that's the third one. Okay? Or what if it wears black Saturday and red Sunday? That's this one right here. Okay? So it's still four possibilities. Okay? And finally, a tree diagram. So we got list, we got table, and let's do tree diagram. Okay, so we got outcomes. Okay, now there's going vertical. I'll do mine horizontal. It'll look a little different. That's all right. Okay, so on Saturday, because that's what happens first, right, in order chronologically. Okay, he could wear red or he could wear black. So that's Saturday. Okay, then Sunday he might wear red or black, right? But branching from his Saturday choice. So here's the Saturday choice, SAT, Saturday, and here's the Sunday choice, SUN, Sunday. Okay? He could go red or black, right? Or maybe if he wore black on Saturday, he could still wear either red or black on Saturday. Okay. All right, so that leads to the sample space. Sample space. Space. Okay. So what were all his outfits leading up to each day? So here's red and red, so that'd be red and red. Okay. Here's red followed by black, RB. Here's black followed by red, BR. And here's black followed by black, BB. Okay. All right. Hey, look, we got the same four. Okay, so here's three different ways of organizing the information. You know, a straight list, a table, or a tree diagram. Either way leads to a sample space with four possible outcomes. Okay. Okay. Example 3. Finite and infinite sample spaces. Classify each of the following as finite or infinite. If it is finite, write the sample space. If it's infinite, classify it, is it discrete or continuous? Oops, get that in frame right there. Okay, and okay, we got 3 examples. Let's do one by one here. Do 3. And so first example, a marble is drawn from a bag that contains 3 orange, 5 green, and 4 blue. Okay, so example 3. Okay. Okay, a marble is drawn. Well, guys, if we're only picking one marble and there's 3 different colors of marbles, I think the sample space would have to be, well, it would be finite, so I'm going to write finite, right? Because you can count the answers. Right? Here's, you can count the possibilities. Okay? So I think it's going to be either orange, green, or blue. So orange, green, or blue. Okay, those are your 3 possibilities. Right? Here, I'll draw this out just so you guys have a picture. Although your book didn't ask you to draw a picture, but we could get 8, 9, 10, 11, 12. I think there's 12 marbles in here, so we get 12 marbles. Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and we can tag a letter to these. Okay? So orange, there are 3 orange. There's 1, 2, 3 orange. There's 5 green. Let's go 1, 2, 3, 4, 5. And there's 4 blue. There's blue, 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 blue. Okay. Okay. But like if you pick a blue one, for example, you have no idea which blue one it is, right? So you can't really distinguish the blues. That's why there's only a sample space of 3 instead of 12. Like now, if you got to identify every individual marble, it's like, oh, this is a very special blue. It's kind of like an aqua blue. This is a dark blue, and this one has a little scratch on it. Right? Okay. Then the sample space could extend all the way to 12 for one for each marble. Okay. But if you don't know, right, then you've got 3 possibilities. Okay. All right. All right, so that was A, right? So now B, let's go on to a different example. Oh, we got a spinner with 4 equal parts. We got green, blue, red, and yellow. Okay, so here, I'll draw this out for you guys. Here, so I'll set a picture. All right, so we got green, blue, red, yellow. All right, spinner right there. Okay. All right, got some spinner that's spinning around. Ooh, give it a little flick. See what color it lands on. Okay. Um, it says it's always going to be spun until it lands on yellow. Until it lands on yellow. Okay. So I think this would be infinite. An infinite number of possibilities, great. Because you might flick it once and it doesn't land on yellow. You flick it a second time, maybe it doesn't land on yellow. What if you flick it 10 times, 100 times? Is it possible you flick this 100 times and it does not ever land on yellow? Yeah, now the probability is very, very, very tiny, but not zero. In fact, same thing with 1,000 times or technically 1,000,000 times, right? And so how many times does it take to land on yellow? Okay. So infinite possibilities, but it would still be discrete because you could count. Maybe you flick it on flick number 1,341. It finally lands on yellow. Like, wow, that took forever. Like 1,341. But that's still a number you can count. That's why it would be discrete. Okay, so infinite but discrete. Now I have a guess that this third example is going to be infinite continuous, but let's find out. A ball is thrown into the air, and its height is recorded in inches. Uh, Oh, you know what? I wish they hadn't put in inches there because if it was to the nearest inch, like the nearest whole number, then that would go back to discrete. Now, if you're allowed to use real numbers, you can go like 4.825 inches. So, okay, actually, you know what? That might be okay. That could be a continuous possibility. So here, give you guys a picture. Take a ball, throw it in the air. Okay, and we're saying what's the height of this ball? Okay, so height as a maybe it's maximum height. Maybe that's what's implied. Okay. So it's not about like how high does the ball go. Okay. But it could really go any height. And if you're allowed to include real numbers, okay, there's an infinite number of possibilities. Okay. And it would be continuous. Continuous. Okay. Again, if you had round to the nearest inch, if it was like the nearest inch, then it would go back to being discrete. And if you could realistically throw some height, like even finite, even right. Okay, so like it's not allowed to reach escape speed or something. There's only so many inches up to up to space, right? Right. But yeah, if you can use real numbers, so say if real, like maybe all real numbers are allowed, are allowed. Right, so we're not rounding to the nearest inch or something like that. All right, let's do see fundamental accounting principle. What is this about? For some large or complicated experiments, listing the entire sample space may not be practical or necessary to find the number of possible outcomes. You can use the fundamental accounting principle. The number of possible outcomes in a sample space can be found by multiplying the number of possible outcomes from each stage or event. Actually, we kind of did that before, but I remember who is this? Was Kembe was wearing these outfits? It was either red or blue, right? Like, okay, so I'm going to link this to this idea that's about to be coming up, which is he had two possible outfits he could wear on Saturday, either red or black, and he had two possible outfits on Sunday, either red or black. Well, what is two possibilities Saturday multiplied by two possibilities Sunday? Two times two is four. And in fact, there were four possible outcomes. Yeah, I think that's what we're getting at over here. Right, so let's see. Example four. This is their last example before the main book puzzles. Example four. We got Santiago lists the number of sections available for courses he will take his first semester at college. How many different schedules did Santiago create this semester? How many different schedules? Okay. Okay. Now I might simplify the assumptions here, assume that none of these classes are going to overlap or conflict or some kind of thing. Right? How many different schedules? Is there some number of courses that he has to take? Okay. Sorry. I think he wants to take all these classes, is what's implied, but maybe they could be in any order. All right, let's see what's up. You can estimate the total number of schedules you can make. There are about 10 sections. 10, 10 of what? Of the okay. That's weird how they have that worded. I don't like that because there aren't 10 of anything. Right? There are 9 math classes. Tell you guys what, I do have the teacher's guide over to the side. So they're saying there are about 10 math sections and there are 9, whatever. Okay. Okay, for each of the other courses, there are about, well, it looks like between 4 and 6. Okay, so about 5 is there. Multiply to estimate the number can create, right? Okay, so, oh, here we go. Here's the number of possibilities in one. Okay, so there are there are 6 different sections you can sign up for in art history. Okay, so we're going to go 6 art history multiplied by, there are 5 different classes that you can take for maybe like 1 p.m., 2 p.m., 3 p.m., and so like different times, right? Okay. He's got to sign up for a math class, and there are 9 possibilities for math classes. You can sign up for any one of those 9. You can sign up for any one of these 4 art classes and any one of these 6 English classes. Okay. So again, I think what's being implied in this situation is that he wants to take all 5 of these classes, but they're all scattered different times of the day. Yeah, right. Right. So what does this exact schedule look like? His exact schedule look like? Right? It could be basically this. Right. So with some simplifications. So let's see what this number comes out to you. Right? I mean, they're telling you it's 6480. I just want to confirm that. So 6 by 5 by 9 by 4 by 6 is, yeah, it is. There's 6,480 possible schedules. Right. Again, assuming that none of the courses overlap, like, oh, what, they're all stacked up at 1 p.m. or something. Right? That might eliminate possibilities, but regardless. All right. All right, what is clothing? Okay, actually, no, they sneaked in another example here. That's all right. We'll do this one. Sneaker company lets you customize your own sneaker on their website. The most popular sneaker, using the most popular sneakers, the base, you have the option to customize the color. They got all these colors. They got 20 colors here. Yeah, 5 by 4, that's 20 colors. Got 20 colors you can choose. Okay. Okay, base got 12. Are these, what's these numbers right here? Um, Using the most popular sneaker as the base. Okay, well, okay. What is the best estimate for the number of possible customizations? Main color 20. Okay. Let's see how to fix that. All right. Let's see what's going on with this one. Okay, so here's what they're doing. I'll just do some one on my calculator screen. So there are 20 colors you can choose. So I'll say 20. Okay. Okay. You can choose any of those 20 colors. Then there are 12 different maybe base designs you could choose. So I'll say times 12. Okay. So you pick one of 20 colors and one of 12 base designs. There are 29 side designs. There are 12 toe cap designs. There are 2 sole designs. There are 29 lace designs. Right. Right, so how many possible combinations are there? And the answer is 4.8 million. Yeah, I'm looking at the teacher's guide, and that's what we're going 4.8 million. Okay. Now, why does it want best estimate? That's so weird they even asked this question. I don't know. I'm sorry. I don't know why they're framing this way. Because the exact answer, and I'm seeing this too, it says it's this number on my screen right here is exactly what they're looking for. Right? Like here, if there were, suppose there were 4.8 million customers, or this number on my screen, that many customers, okay? They could each get a unique pair of shoes that looks nothing like anybody else's shoes. It could be possibly the case. Okay? But if you added one person to this list, so you have 4,844,161 people, right? Now somebody has to have the exact same shoes as somebody else because we're out of combinations at that point. All right, let's hit these book puzzles. So I highlighted some ahead of time. Number 4, spinners. Number 4 here. We got this, what's the sample space for the spinner? Ooh, sample space right here. So I'll say S equals. Now this looks discrete, so I'll use curly brackets and I'll just list all possibilities. It could be either A, B, C, D, or E. Right? Those are the letters. Right, that's it. Okay, that was the question A. And then there's also question B. It says, what's the sample space for landing on a vowel? So sample for a vowel specifically. Right. Well, I see A is a vowel and E is a vowel. And that's it. So there's 2 possibilities. Yeah, that's right. Okay, number 5, uniforms. For away games, the baseball team can wear either blue or white shirts and blue or white pants. Represent the sample space with a table, a tree diagram, and an organized list. Hey, isn't that actually identical to example 2? Remember, Kembe could wear a black hat or a red hat on Saturday or Sunday. I think this is not going to be significantly different than that. So example 2. Okay. Let's go with, let's start with complete a table tree diagram. Let's do a table first then. Okay, so table, as they prompted a table first. Okay, blue or white, blue or white. Oh, sorry, it's not a Saturday, Sunday thing. Okay. It's either a shirt or pants. Okay, that's okay. It's gonna be really similar. So we can go shirt, we can go pants. Okay. And for the shirt could be either blue or white, and the pants could be either blue or white. Okay. So they could go blue shirt, blue pants. They could go white shirt, blue pants. You could go blue shirt, white pants, or they could go white shirt, white pants. Okay. Let's do tree diagram. So tree diagram. So you have to pick. Okay. So I'll say start with outcomes. Okay. I'll do this one vertical because I did the last one horizontal, but you're both doing these vertical anyway. Okay. And so here, start over. Okay. So 5B. Okay. Okay. So all right, outcomes. Okay. Let's go shirt. Okay. Now you can choose either a blue shirt or a white shirt. Okay. And then it's going to branch off from there to pants. You can choose either a blue or white set of pants. Okay. Okay. So then that leads to, well, the organized list. Okay. So this is the tree diagram. So tree diagram. Okay. Now let's do organized list, which is the next step of this tree diagram anyway, which is say the sample space is, and we got 4 discrete possibilities. Could be blue, blue, so blue, blue, could be blue, white, could be white, blue, could be white, white. Okay. Now these are all individual because from the first letter applies to shirts. So shirt, 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 shirt. Okay. And the second letter applies to pants. So pants. Okay. So what I'm trying to get at there is blue, white, and white, blue are 2 different things. Right. Okay. So they're not the same thing. All right. So there you go. That's all those. Auditions. The drama club held tryouts for 6 roles in a one-act play. Got 5 people audition for lead female, 3 for lead male, 8 for best friend, 4 for mother, 2 for father, 3 for humorous aunt. How many different casts can we create from those who audition? Okay. And I'm going to do a simplifying assumption here and assume that these are all different people, so they're not overlapping. For example, if you got the lead for lead female, you wouldn't also be auditioning for humorous aunt because that would maybe conflict with that. So don't worry about that. Right? Maybe that'll be more complicated later, possibly. Right? So I think this was one where we can multiply these together. They had a term for that. It was called fundamental counting principle. Here, I'll go ahead and spell that out. It says, yeah, you can multiply. So I'll spell out that phrase. Fundamental counting principle. Okay. So let's multiply all the numbers together. Okay, 6 roles. Okay. We can do 5 people audition for lead female. Okay. Now there's 5 possibilities, right? Because any of those 5 could get the role. Okay. Then we're going to multiply that by there's 3 lead male. Okay. So any of those 3 could get the role. Already we're at 15 possible different casts. Right? Any one of these 5 people, any one of these 3 people. Okay, that's 15 possibilities for the 2 lead roles. Okay, got 8 best friend, so there's 8 possibilities on that dimension. 4 possible mothers, 2 possible fathers, and 3 possible humorous aunts. Okay, there's all 6 roles. So if we just simply multiply this out, that will tell us how many possible ways it is to cast. Okay, so 5, 3. Yeah. 8, 4, 2, 3. Okay. So I'm looking at 2,880 possible casts. Okay. Now, if you wanted to write out the full sample space, right, that would take all day because you'd have to write 2,880 probabilities, right? like Tim gets this role, and Susie gets this role, and John gets this role, and so on all the way down. Okay. Could be one possibility, and there would be 2,880 possibilities. Okay. Number 22. Ooh, license plates. 22 license plates. Okay. The state requires license plates to consist of 3 letters followed by 3 numbers. So I'll give you guys an example. How about 3 letters could be like M, N, Q. Okay, so we need 3 letters followed by 3 numbers. So it could be like 0, 6, 7, 3 number. Or wait, no. All right, I'm gonna end this. They say the letter O and the number 0 may not be used. So let's just change this to an 8. There we go. 867. Looks better. So that could be one possible license plate. License plate. Okay. And they want to know how many different license plates can be created. How many different possible license plates? So possible license plates. Okay. I think I can still use this fundamental counting principle. I can still do that. Okay. We'll just do this for each character, 6 characters. Oh, just like there were 6 people auditioning for the play. Okay, so that's kind of fun. Okay. Now, I'm going to also assume that it's okay to use 2 or 3 letters in a row. Like it could be M, M, M is okay. Okay, so I'm not going to disclude anything like that. What we do have to disclude is the letter O and the number 0. And if that's true, then out of these 3 first letters, well, there's only 25 possibilities here and here and here individually, okay? Because there's 26 letters, but we're throwing out O. So the 25 times 25 times 25, right? And then multiplied by, and then the numbers. Now there's 10 different digits, but we're not allowed to use the number 0. So really, it's only 9 possibilities. So there's 9 possibilities on the first one, 9 on the second one, and 9 on the third one. Okay. Now, again, I think in the real world, it's a little more complicated because maybe you want to throw out some possibilities. Like, probably not very many people want the tag 666, which would be one of these 2. Right? But we're going to include it in the possibilities here according to this set of rules. We're only throwing out the O and 0. So let's do 25 to the 3 times 9 to the 3. Okay. So this looks like, ooh, that's a lot of possible license plates. 11 million. Possible possibilities. Okay. Got 11 million possible license plates. Okay. So if you were living in a state that had a population that was larger than this, or I should say the number of cars on the road, right? The number of cars on the road is more than this. Well, now you're out of license plate possibilities. Okay. So so then you have to do something like maybe change the rules. Like, okay, well now we got to allow some letters in the second string, some numbers in the first string. Otherwise, we only got 11 million plates to get out. Okay. Now let's do one more example here. Biking. You got Tallulah. Got a new bicycle lock with a 4-number combination. Okay, so I'll spell that out. 4-number combination. Each number could be anywhere from 0 to 9. Okay, so includes all the possible digits, 0 through 9. How many combinations are possible if there's no restriction on the number of times that Tallulah can use each number? So if she wants something like 5, 5, 8, 5, that would be okay. She can repeat digits. Okay, okay, so no restrictions on the numbers she can use. Okay. So for the first here, I'll kind of give you guys a visual here as an example. So I'll say, for example, could you do 5, 5, 8, 5? It would be one possibility. Okay. Well, I think in the first digit, there's 1 of 10 possibilities. And the second digit is again 10 possibilities, and so on all the way down. Okay. So that's 10 to the 4, or was that 10,000? Possible combinations. Okay. 10,000 possibilities. Okay. Now there's a follow-up question though. Part B. It says how many combinations are possible if Tallulah can use each number only once? Each number only once. Let's do another example then. Okay, so I got 4 digits. Say, well, geez, it could be anything, right? But not quite anymore, right? Because like this example I did before, is not allowed because 5 is used more than once. Okay, so the first digit can be 5, but not the, but now we've expended the 5. Ooh, but now we got to pick a different number. How about how about 0? That's okay, right? So it's not 5. Okay. How about now if you're keeping track, right? See, before there were 10 possibilities on each digit. Right? Now in this new example, the first digit could be any of the 10 digits. That's okay. But the second digit, well, we've eliminated one of the possibilities. So now there's only 9 remaining. Only 9 remaining because we can't use the 5. By the time we get to the third digit, now we've expended 2 numbers. So you can't use the 5, you can't use the 0. So now there's only 8 possibilities. And then by the time you get to the fourth digit, well, we've expended 3 numbers out of the possible 10, which means we're down to 7 possibilities. Right? Something like that. So I think there are going to be not as many possible combinations allowed. 10, 9, 8, 7. Okay? And that is 5,040 possible combinations. Okay. Actually, since we're talking about combination, I mean, it's literally a combination for like a combination on a lot. Okay? But combination is also a math term that applies exactly to this, right? We might eventually do that, and the calculator can calculate this too. Let me try this. All right, let's do. Oops, let's do. Here we go. Now I'm thinking of it. This is being more of a permutation thing. Like I said, this is an extra. This is like a bonus note. Right? It's called permutations. If the order matters, right? Like here, if you didn't care about the order of the numbers, like okay, if there's a 5, 0, 6, and 7 somewhere in the mix, but it could be in any order. It could be 6, 0, 5, 7. That'd be okay, right? That would be what's mathematically called a combination. Right? But if the order has to be distinct, which would be true for a bicycle lock, right? It has to be in this order. Like 5 has to be first. Then they call it a permutation. Right? And the math phrasing for this goes. Let's see, we got n possibilities, and we're going to do factorial, which is 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1. We got to do, no, but we got to divide by the number we're choosing. Okay, so in this case, this would be, we got 10 numbers, okay, but we're only going to choose 4. Okay, okay. And if I do that, I get 10, say 10, 9, 8, 7 over 4, 3, 2, 10, oops, 9, 8, 7, 4, 3. Okay. So this would be here 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 over. Okay, we're choosing 4 possibilities, which is like okay, sorry, I gotta do this. I gotta do I remember what it is. It's n minus r. That's right. N minus r. So we'll do 10 minus 4. That's what we'll do. Okay. 10 minus 4 is 6. Right. 6 factorial is like 6, 5, 4, 3, 2, 1. So most of this cancels. All this cancels. We're left with 10, 9, 8, 7, which is exactly what we have here, and it matches. Right. But there's another way you can get it in your calculator. Is you can type the number 10, and then there's a probability key, PRB, point, and then keep in PR for permutations because we care about the order of the numbers, and then type 4 because we're 10 possibilities on each of these. We're going to choose 4 numbers. Okay. It also tells you 5,040. It'll do it for you. Okay. So yeah, show up in the future, but there you go. There's an intro to probability and sample spaces.